The Biot Savart law. The Biot Savart law answers the question, what is the magnetic field created by a current carrying wire? So if this is an arbitrarily shaped current carrying wire here, remember that the S vector points in the direction of the current. If we look at a radial distance r from this segment of the wire, what will be the magnetic field due to this current? First of all, we point our thumb, right hand thumb, in the direction of the current. The four fingers curl into the page on the right hand side and out of the page on the left hand side. So we see that the magnetic field points into the page at this point P prime and out of the page at this point P. So your thumb points in the direction of the current, four fingers will be on the left side pointing out of the page, curling towards you. So that's basically saying the magnetic field lines are curling around this wire like this. Now, how do we calculate the magnitude of this magnetic field? That's given by Biot Savart law, mu0 permeability of free space divided by 4 pi times the current ds cross r hat over r square, where r hat is a unit vector that points from the line segment towards the point of interest. Now this is basically similar to the electric field due to a charge 1 over 4 pi epsilon 0, which is k, the Coulomb's constant, dq over r square in r hat direction. So it is similar to the electric field. Now the experimental findings are that the magnetic field due to this current carrying wire is perpendicular to the length vector here, ds vector. Ds vector points in the direction of the current, and so the magnetic field is perpendicular to the current. The magnetic field is perpendicular to r hat, where r hat is a unit vector from vector ds to point P, so it's also perpendicular to this vector. It's perpendicular to ds and r hat, therefore it's perpendicular to the plane that contains these two vectors. So it's the cross product, ds cross with r hat. The magnitude dies off as 1 over r square, where r is the distance between ds and the point of interest. The magnitude is proportional to the current and it's proportional to the length ds. And it's also proportional to sine of the angle between the ds vector and r hat vector. So magnetic field at this point is basically proportional to sine theta, for example. So mu0 permeability of free space is 4 pi 10 to minus 7 Tesla meter per amperes. Then the total magnetic field at B created at a point P due to a current is the sum of all contributions from all current elements from all such ds's. We add them up, we obtain mu0I over 4 pi integral throughout the current carrying conductor ds cross r hat over r square. So we sum up the contribution from all current elements. Now if we compare electric field with magnetic field, we see that the r dependence is the same. The electric field due to a point charge dies off as 1 over r squared. The magnetic field due to a current element dies off as 1 over r squared. The electric field is due to a point charge. Magnetic field is due to a current carrying conductor. Electric field direction is in the direction of r hat, but the magnetic field is perpendicular to the plane that contains ds vector and r hat vector. Therefore, it's perpendicular to the current and the r hat vector. So that is basically reflected in this cross product. Okay, so here we have introduced Biot Savart law that describes the magnetic field created by a current carrying wire. If we have a current element with length vector here, ds vector, pointing in the direction of the current, and r hat is the unit vector that points from the current carrying segment towards the point of interest, we have ds cross with r hat divided by r square, the distance between the current element and the point P squared, multiplied by mu0 over 4 pi, where mu0 is permeability of free space 4 pi 10 to minus 7 Tesla meter per ampere. It is the magnetic field due to this current element. If we add up the contributions from all current elements, if we integrate it throughout the wire, we obtain the total magnetic field. We see that the magnetic field is perpendicular to ds, perpendicular to r hat, scales as 1 over r square, proportional to current and the length, and is proportional to sine of the angle between ds vector, the current direction, and the r hat vector. And if we compare it with the electric field, we see a similar r dependence, dies off as 1 over r square. Electric field is created by this point charge here. Magnetic field is due to current carrying conductor. The direction is different. The direction is in r hat direction for the charge q. In the case of magnetic field, it's perpendicular to ds vector and r hat for a current element which has length vector ds.